All right, so acids and bases is often one of the last topics that's taught in Chemistry 14A, and it's actually one of the most important. It shows up very often on final exams, and it turns out that acids and bases is very involved. There's a lot going on, so really important to keep in mind. This video will sort of introduce the basics of acids and bases. So first off, definitions, right? There's kind of two competing definitions. One is Bronson-Lowry and the other is Lewis. Bronson-Lowry focuses on the proton, right? And so here we define an acid as something that donates a proton, where a proton is a hydrogen plus ion, a base is an acceptor of a proton. So a common example would maybe be like HCl, right? Hydrochloric acid is a proton donor because it donates that hydrogen. A Lewis definition focuses not on the proton, but the electrons, the lone pair. So an acid, instead of being a proton donor, it's an electron acceptor, and a base is a lone pair donor. So it's sort of the opposite. You should know both of these definitions. The second thing you should know is what the difference between strong and weak is. All right. And a very common misconception is that strong and weak has to do with concentration. So for instance, a common misconception is that something that's 10 molar is very strong and something that's 0.1 molar is very weak. That's completely wrong, right? Strength has not to do with concentration, but rather an inherent quality of the acid or base. So something that's strong completely dissociates in solution. Hydrochloric acid, HCl, is an example of an acid that completely dissociates because HCl becomes H plus Cl minus in solution. And 100% of the HCl dissociates into its two ions. Whereas for a weak acid or a weak base, for instance, a common example is acetic acid, which is HC2H3O2, is a weak acid. And so instead of writing a one-way arrow, we write a double-sided arrow to signify that not all of it dissociates. Dissociates into its ions, right? It's H plus and its conjugate base, but not completely. And because it's not complete, and because there's an equilibrium, we specify an equilibrium constant, Ka for acid, Kb for a base. So essentially, a strong acid or strong base will never have a Ka or Kb, or in other words, you won't need to use it for those problems. The last thing you need to know is what pH means and how to calculate it. So P of anything just means minus log of. So if you take pH, that means you might take the minus log of the concentration of H plus. There's something else called a POH, which is just the minus log of the OH minus concentration. Remember that H plus is acidic, whereas OH minus is basic. And if you sum pH and POH together, you get 14. So if you know one, you can figure out the other. All right, so let's just do some examples. So let's calculate the pH of a couple strong acids and strong base. So let's start with HCl. So we know if we write out the dissociation that we get something like this. HCl makes H plus plus Cl minus. And what happens is that this is a one-way reaction. All of the HCl dissociates into its two ions. And so the concentration of H plus is actually equal to the initial concentration that you had, 0.2, because all of it gets dissociated. And so if you take the minus log of this guy, which is how you figure out pH, and put it in your calculator, basically the minus log of 0.2, you would get a value of 0.7, right? And it turns out that is going to be your pH. Very, very low. Remember, anything that with a pH lower than 7 is very acidic. This is super close to 0, actually, and so it's highly acidic. We can do the same thing for NaOH. So the first thing I do is write my dissociation of the base. NaOH goes to Na plus OH minus. The OH minus is what causes it to be basic. Here I'm going to calculate the POH. So I know the OH minus concentration is going to be equal to 0.1 molar because all of it dissociates. So I take the minus log of OH minus, which is equal to minus log of 0.1, and that actually gets me a value of 1. Now, because I took the minus log of OH minus, this represents my POH, so in order to get my pH, I take 14 minus 1, gets me 13. And so here it's a base, very high pH, which is exactly what we'd expect. So strong acids and strong bases tend to be a little bit more easy than weak acid, weak bases. So we'll try some of these examples, and we'll see that we actually have to use ice tables that we've seen before. All right, so let's start with 0.4 molar HCN. They give us the Ka value. All right, so as usual, I'm going to write my dissociation reaction. HCN goes to H plus and Cn minus. And what I'm going to do is draw my ice table. So initial change in equilibrium. And initially, I have 0.4 molar, 0, and 0 of the H plus and Cn minus. I lose some of this guy, and then I gain the H plus and the Cn minus, so that gets me 0.4 minus x, and an x. I can write my equilibrium constant as the products over reactants, so I can write 6.2 times 10 to the negative 10 is equal to my products all over my reactants. And here what I can do is instead of having to use the quadratic, I can assume that x is very small. So assume x is small. And what that allows me to do is bypass using the quadratic formula. So I can basically get rid of this term. I'll keep the term on top because I still need to solve for x. I multiply both sides by 0.4. I take the square root of that value, and I should get x equals 1.57 times 10 to the negative 5. And that is equal to my concentration of H plus. And so if I take the minus log of that, of 1.57 times 10 to the negative 5, I get my pH, which here turns out to be 4.8, which is actually what we would expect because it's an acid, but not as strong as before, right? Remember, that's a weaker acid, so the pH is a bit closer to 7. All right, so number 4, calculate the pH of this guy, ammonia, 0.3 molar NH3, and they give you the Kb, right? So we're just going to do the same thing, write the dissociation of this base. Turns out that for ammonia, you need to write the dissociation reaction in the presence. Oh, by the way, this should be a double-sided arrow because it's a weak acid. You need to write H2O. So what do bases do? Well, according to the Bronson-Lowry definition, they accept protons, and so it's going to steal a proton from the H2O. It's going to become NH4 plus, and then what's left of the H2O is going to be OH minus. And so the OH minus makes sense because you know that NH3 is a base. Then we do our ice table. We know that we start with 0.3 molar of NH3. I don't have to take care of the H2O because there's no concentration associated with it. 0 and 0 for the NH4 and OH minus, minus x, plus x, plus x. And so I fill in my equilibrium concentrations, write my expression for the equilibrium constant, which is 1.8 times 10 to the negative 5, is equal to x squared all over 0.3 minus x. Here I'm going to assume that x is very small, so I can basically get rid of this term. I multiply by 0.3, divide by, I take the square root of that resulting term, and I should get an x value of 0.0023. And that represents, here in this case, my OH minus concentration. All right, and so if I take the minus log of this guy, I get my POH, so minus log of 0.00232 gets me 2.63, but that's my POH, so I have to take 14 minus that guy. 2.63 gets me 11.37. So my pH is 11.37, what you'd expect because it is a base. All right, and then the last thing that I'll talk about is the conjugate seesaw, which really is, which should actually make intuitive sense. So if you're looking at an acid, weak acids have strong conjugate bases. So basically, the weaker the acid, the stronger the conjugate base. The converse is true. The stronger the acid, the weaker the conjugate base. So when you're looking at actual strong acids, things that completely dissociate, the conjugate base is so weak because the acid's so strong that the conjugate base actually does not have any basic qualities. For instance, if you look at HCl, HCl is a strong acid. The conjugate base is Cl minus. Cl minus has no basic properties. So I can say not basic. So Cl minus by itself will not affect the pH of a reaction or a given solution because it's the conjugate base of a strong acid. And because the acid's so strong, the conjugate base is very weak, it's not basic at all. Same is true for bases. So weak bases have strong conjugate acids, and strong bases have weak conjugate acids. The same is true as before. The conjugate bases of strong bases are not acidic. So an example of a strong base that we've seen before is NaOH. The conjugate base of NaOH, the conjugate acid of NaOH is Na+, so Na+ is not acidic, right? Because it's the conjugate acid of a strong base, and so it's not acidic, so it won't affect the pH of a reaction. All right, so using that information, let's try to apply it to this problem. So it says the conjugate base of which of the following acids has the lowest pOH? So what does that mean? Low pOH means high pH. So we're the highest pH. And then what does highest pH mean, right? Things that are closest to 14 means that it's the most basic, right? So in other words, they're asking which of the following conjugate bases is the most basic? So highest pH means most basic. So let's look at what we have here. If we're looking for a conjugate base that's the most basic, we're looking, the acid that will have the most basic conjugate base will be a very weak acid. So what we're looking for is the weakest acid, because the weaker the acid, the stronger the conjugate base. So which of these guys is the weakest? Well, here HCl is a strong acid, and that's why the Ka is unspecified, so that's not going to work. And basically the Ka value is a measure of how much an acid dissociates, and thus it's a measure of the strength of the acid. And so essentially we're looking for the Ka that's the smallest value. So smallest Ka. And so the smallest Ka, it's not going to be this one, not this one, but rather the last one, H2CO3. So the conjugate base of this guy would have the lowest pOH, highest pH, and be the most basic.